So yeah, in this work, I will follow the papers that are written here. From some initial work with Andrew Childs and Robin Gottari in 2017, more recent work on quantum algorithms for this problem based on adiabatic evolutions with Ige Subasi and David Orsuji, and more recent work on quantum state verification. This last work kind of like gives some evidence why some ideas, that were proposed for this problem recently may not work, and that is hard to get, fortunate and solve this problem using less resources than what we already knew we needed somehow. So I'm personally not that good at keeping track of the chat. If there are some questions that come up, and have to be answered during my talk, I'm happy to do so. If not, I'll answer them at the end. Some of the work that I present, it will be at a fairly basic level, and my hope is that pretty much everyone can get something out of this talk. All right, so what is the linear system problem? Well, here we are given some matrix A. We might assume this matrix is symmetric, Hermitian. It's an n times n, big N. Think of this dimension as being extremely large. There is a vector B, and your goal is to solve for AX equal to B, find such an X. Classical algorithms for this, even the best classical algorithms, as you might expect, have a complexity that certainly will depend on the dimension of the matrix or the vectors. This is because it will involve some sort of arithmetics like matrix vector multiplication, addition of vectors, and so on. So certainly there will be some sort of dependence, at least linear in the dimension, and the best general purpose classical algorithm is known to be the conjugate gradient is indeed linear, at least in the dimension, and scaling with the square root of kappa. Kappa is the condition number. The larger kappa is the harder it is to invert the matrix. So that is going to be an important parameter here in the complexity of its algorithms. The quantum linear system problem is saying somewhat differently, because the goal here is to really avoid that scaling that is polynomial in the dimension n, big N. And the way the problem is formulated in the former paper by HHL is that the goal is to actually prepare a quantum state X that now encodes the solution to the linear system. And the encoding is in the amplitudes, these Xi's that are here. This state might be normalized. This is the former definition of the problem, but in other definitions, that is not the case. So specifically for a given precision parameter that I call epsilon, the goal of the quantum linear system problem is indeed to prepare a quantum state, ρ of X, that it might not be necessarily pure, it might be a mixed state, such that its trace distance with the actual solution X that we're seeking here is upper bounded by some epsilon. By putting this condition on the trace norm, then you're guaranteed that if you do any experiment with ρ of X or X, you won't be able to distinguish those two things with probability larger than epsilon. All right, so why is this problem interesting? And honestly, sometimes I still ask that to myself. But we might argue that linear systems are important in science, engineering, and more. So it is natural to try to see whether a problem related to solving systems of linear equations can be done with a quantum computer. Quantum computers are known to provide exponential quantum speedups, so maybe there is some sort of exponential speedup for this linear algebra problem as well. So it's certainly worth investigating. But beyond studying systems of linear equations, I think that studying new problems and how to solve them with quantum computers sometimes result in very nice and new algorithmic primitives that might be used for other quantum algorithms as well. So this quantum version of the problem is, as you know, only useful for computing expectation values in the solution of the system, and really not for obtaining the actual vector. That would take time that is at least linear in the dimension. So we're back to this polynomial scaling then. So are there any interesting applications where all these conditions and requirements are useful? Certainly that's open to debate. There's been some discussions so far in this conference today, and I'll mention a few other things later in mind. So this, you might want to read this paper, read the fine print, where they discuss what the limits of algorithms like this are. All right, so we are going to make some assumptions. I'm going to enter to describe a little bit how these algorithms work. So we're going to make some assumptions and explain a little bit about what are the queries in this quantum linear system problem. First, I'm going to assume that the matrix is Hermitian. This is kind of like with no loss of generality. the spectral norm of it, I'm going to bound it by 1, or I make it just 1, and I'm going to think that this dimension big N is exponential in some little n, and that little n might be related with some, number of qubits in some Hilbert space and so on. Certainly, the matrix is going to be invertible, and there's going to be a condition number, and the condition number is the ratio between the largest and the smallest singular values. Okay, this is what I call kappa. I'm going to assume that that kappa is less than infinity, so the matrix can be indeed inverted. In terms of queries, I'm going to assume that there is a couple of procedures here. These are, you may think of those as being unitary operations. There's one procedure, use of A. What it does is like given a label for the row and the column of the matrix. It computes the element of the matrix in some additional register. It also gives the location of those matrix elements, the ones that are non-zero. This makes sense whenever the matrix is sparse. So we might assume that the matrix is sparse as well here. And these are standard requirements, or standard procedures are used in quantum algorithms. There's going to be another procedure that I call the state preparation procedure, use of B. What it does is when applied to some 0 qubit state, it prepares state B that is proportional to the vector B, in the sense that it's now normalized, and those amplitudes are encoded. The entries of the vector are encoded in the amplitudes of the vector, of the state. So for simplicity, these procedures are usually considered as black boxes. We don't look at the inner workings of it. Eventually, in applications, it will need to be implemented using 2 qubit gates, but we abstract away all their, how they work. They're useful because many times by think of these black boxes, we can place lower bounds on the complexity of solving the problem in a black box model. And here I'm going to assume that they can be implemented with constant time, and the number of uses of these UAs and UBs is what they determine the so-called quantum query complexity of the algorithm. Sometimes people separate between the different query complexities, how many UAs you need, how many UBs, or even the gate complexity. But at the same time, the number of queries, the number of times you need UA or UB, also give you a hint on what to expect for the gate complexity in an actual application. All right, so there's been a number of improvements along the years for this quantum linear system problem. For the former HHL algorithm that achieve an scaling quadratic in the condition number, polynomial in the inverse of the precision, to something unbiased. He described this new technique, variable time amplitude amplification, to make the scaling condition number to be linear now. Some improvements by Robin Kothari and Charles and myself on how to improve the scaling precision to something that is polylogarithmic in 1/epsilon. Some other approaches based on adiabatic evolutions by myself, Igit, Subasi, and Orsuchi, and even some people, Anna and Lynn, that are here in the conference, improving the algorithm, these adiabatic algorithms that we were thinking of a number of years. Each of these algorithms use different techniques like quantum phase estimation, Hamiltonian simulation, variable time amplitude amplification, and so on. And hopefully I have time to describe a little bit how these things work, at least at the high level. So the rest of the talk is high-level idea for the HHL algorithm and one of our quantum algorithms for this problem that exponentially improves the dependence in the precision. I'll make a quick comment on applications, and then I present some recent results on the limits of variational algorithms and other algorithms for solving this problem, and why we suspect they won't work. All right, so what is the general idea that we typically use for the quantum linear system problem? You probably saw this already in some other talks. Well, here, it's simply the observation that the state that we want to prepare can be seen as the inverse of the matrix A acting on the vector B. Okay, so if I can prepare the vector B and somehow implement this non-unitary operation, which is the inverse of A on it, on that, then I'll get the state basically that I want. This is a non-unitary operation, and therefore, typically what we typically seek is to encode it in a block of a bigger unitary matrix. Okay, so by doing so, when we apply such a unitary to the initial state and maybe some 0 state for some ancillary register, then we have 2 branches of the state, one that encodes the right solution, and another one that I call it trash, is not useful. And the next step would be either to measure the ancilla or to do something like amplitude amplification to amplify the right part of the state that we are, our target state. So the HHL algorithm kind of like works like this. It implements, that inverse operator in the initial state. using the quantum phase estimation algorithm. Quantum phase estimation gives you an estimate for the eigenvalue of A, and then what you do is some sort of conditional rotation on the ancillary qubits such that the amplitude in some zero state is indeed proportional to the inverse of the eigenvalue. Then you do amplitude amplification, okay? And after a certain number of rounds, you could expect that the probability of getting the right solution is high. So it's fairly simple to compute, to estimate what the complexity of this approach is. It's going to be given by the number of amplitude amplification rounds times the complexity of each quantum phase estimation algorithm. And if you put everything, take into account all the details of the algorithm, scales almost quadratically in the condition number and the inverse of the precision parameter, as explained at the beginning. The other approach that we came up with to improve the scaling in precision is based on linear combination of unitaries, this LCU algorithm. Okay, so there what we've done is to take a different view. We thought of the inverse operator as being some sort of linear combination of unitaries. The unitaries here with a Fourier transform approach. There's this identity that we thought it was going to be useful for this because it has some nice properties in terms that there is an exponential decay of these amplitudes. Think of this as being unitary operators. And the amplitudes in linear combination are rapidly decaying, so we can cut off the integrals fairly fast. And at the end, the result is that the inverse operator 1 over A can indeed be written as a linear combination of unitaries. These are the amplitudes here in the linear combination times unitaries that correspond to evolutions under operator A for different times. Okay, the times here would be the products of Yj times Zk. These are real numbers. Okay. So there's another nice feature of this approach, which I think it is worth emphasizing, is the fact that we are now reducing the problem of applying the inverse of the operator to one of Hamiltonian simulation. And even though there are techniques for block encodings and so on, I personally think of the problems like Hamiltonian simulation 1 is going to be useful for finding quantum speedups. This is because we have so much theory, so many tools for Hamiltonian simulation in particular that do not require this block encoding or necessarily require this block encoding. That can be really useful to implement these Hamiltonian evolutions fairly efficient. One example would be, for example, fast forwarding the evolution. Okay. It turns out that when you do this decomposition, the maximum evolution time that you need to achieve precision epsilon actually scales polylogarithmic in the inverse of the precision parameter. And this is the main reason why we get that exponential improvement in precision with respect to the HHL algorithm. So if you do this approximation, this discrete sum, and you plot things, you'll see that the inverse function 1 over x is fairly well approximated by that. But that sum up to some point, and we set that point to be related to the inverse of the condition number, because that's the only place where we want to approximate. All right, so at that point, we have the inverse operator as a linear combination of unitaries. We developed this LCU framework. Some of you might know already about this. The idea is that if we have some quantum state, now we want to map that quantum state or act with a linear combination of unitaries here, alpha V1 plus beta V2. V1 and V2 are unitaries. And, there's this nice primitive that does the job. You put an ancilla, the ancilla encodes now the rotation, encodes the amplitudes in the linear combination, and you fire one of the unitaries, condition 0 or 1, and the other condition in the other state, and then you invert that operation. And at the end, you can see that the state that you have is actually something that contains the right part of the state and what we call before trash. So if we make a measurement here, then we would obtain the right linear combination of unitaries acting on the state. This is going to happen with some probability, but in reality, to improve that quadratically, we use the standard technique of amplitude amplification. All right, so the complexity of this LCU approach is mainly given by the number of amplitude amplification rounds now, times the complexity of implementing each of the LCUs. Okay, you can go through the analysis, but basically the idea is that if the largest eigenvalue is 1 and we're applying 1 over kappa A to the initial state, we will need this number of rounds of amplitude amplification because this is the inverse of how much we are reducing the round. Okay, this is linear in kappa in the worst case. And again, because the smallest eigenvalue is 1 over kappa, we'll have to evolve, in our analysis with A for time that is at least linear in kappa. And at the end, if we do this approach, we can recover this quadratic scaling in the condition number, but we improved a lot in terms of the precision. This is what is shown in that. The nice technique of variable time amplitude amplification introduced by Ambanis allows you to go from this quadratic scaling in kappa to something that is linear in kappa. It can be seen that the quadratic scaling in kappa is coming from like these two like opposite limits that they don't happen at once. One is because of small eigenvalues, and the other one is because of large eigenvalues. The round number of amplitude amplification rounds can be large. And we're assuming also that the complexity for implementing, for example, each LCU is large, but those two large occur at in different limits. So the variable time amplitude amplification technique, considers this in some way, and what it does is partition the problem into different regions. It splits your original state. It has some register that tells you, well, this part of the state is supported on large eigenvalues, this part on eigenvalues in the middle, and this part on small eigenvalues, and you do things by stages. First, you apply the inverse operator to the large eigenvalues part, and then smaller eigenvalues, and so on. And each of these implementations can be done with different precision. Okay, and when you put everything in the bag, you can show that indeed you have that sort of improvement from quadratic to linear in the condition number. And this technique, we did use in our LCU paper, this technique to improve the scaling to something that was linear in the condition number. All right, so last I'm going to describe, again at the high level, this adiabatic spiral algorithm. So this VTAA technique is somewhat a little bit complicated. It requires many steps, amplitude estimation, requires many ancillary systems, and so on. Okay, so we came up with this nice idea that, well, maybe there was some sort of adiabatic approach that could solve the problem, and perhaps we could obtain this nice scaling that was linear in the condition number without requiring so many ancillary states or so many complicated subroutines. And indeed, this is what we showed in a more recent paper with Igor Subasi and David Osorti. So the idea here was to say, we create a Hamiltonian path, and the Hamiltonian has some eigenstate. And we want to drive some simple eigenstate associated with the initial Hamiltonians to some more complicated eigenstate of a final Hamiltonian that encodes the solution. In this case, it's going to be exactly X. It's kind of like going from solving a simple linear system of equations to a more complicated one, which is the one that we want. To drive that original eigenstate to the final one, we implemented the so-called randomization method. It can be thought as a quantum Zeno method in which we perform projective measurements, or we simulate projective measurements at very nearby points. And by doing so, you can show that you are driving the eigenstate to the next eigenstate, and so on. And at the end, you can achieve the final eigenstate with high probability if you have enough points in the discretization. How we build the Hamiltonian? Really simple. We took the linear system AX. It has to be equal to B. Therefore, the orthogonal projector acting on AX has to be equal to 0. This allows us to build some operator B, and that acting on X has to be 0. And our Hamiltonian has some form that encodes B in each of the blocks. We made it Hermitian. And now we do an interpolation for the path where we start with some initial matrix A of S that is exactly the identity, and we map it to something that is exactly the A matrix that we want to do. And this is basically simplification what I was saying before, going from some simple linear system to a more complicated. All right. When you do the analysis of this method, you will see that, the complexity is going to be given by how many times you need to do the measurement, by times what is the complexity of simulating each of the measurements. Each of the measurements is simulated by evolution randomization. We need to work with the Hamiltonian for some random time, and that random time has to scale with the inverse of the gap. The number of points we showed in that prior work that has to scale quadratically with the length of the path. So what we showed in this 2019 paper is that the path, this length, is actually logarithmic in the condition number. So it doesn't introduce a big scaling, polynomial scaling in the condition number. And we show that the spectral gap can never be smaller than the inverse of the condition number. So when we take a look at the whole complexity and use this formula, you obtain the complexity is almost linear in the condition number and inverse in the precision parameter, and that can be further improved. All right. Okay, so this algorithm actually has been randomized by Ann and Lin in that other work that I showed at the beginning by coherent adiabatic evolution that achieves actually a better scale in terms of the path. All right, so why are these improvements useful? Well, we were able to develop optimal algorithms for the quantum linear system problem using significantly less resources than previous approaches. We didn't need to implement anything like variable time amplitude amplification. It was just using a simple adiabatic approximation to show that that we got the right scale. So these improvements in general, not only for the adiabatic approach, but also for the LCU approach and other approaches based on Chebyshev polynomials, actually allowed us to prove polynomial quantum speedups for example, the problem of hidden time estimation of a Markov chain. If we didn't have that improvement in terms of precision, then we were not going to be able to show that result. Okay, so these are some hints that these improvements are actually useful. Having small complexity and dependence on precision is always important, especially for the quantum algorithms. Many times it is the case that their complexities scale pretty badly in terms of the precision parameter. And in addition to that, if we are aiming at computing some expectation value of an observable, we'll have to run the state preparation so many times to decide to find to achieve the desired precision at the end that you really want to improve the complexity of the algorithms as much as possible. Without the polylog dependence on precision, for example, then you wouldn't be able to achieve the so-called quantum metrology limit, where computing the expectation value, some expectation value of an observable on some state, the scaling goes with the inverse of the precision parameter alone, and not inverse of larger powers of that precision parameter. So these improvements are certainly useful in that regard. All right, so as I said, these algorithms have scaling that is polylog in the dimension n. So somehow we claim that it's an exponential speedup, but in reality, as I explained before, these algorithms do not output the full vector. All right, so it's a contrived problem in that sense. There are some applications, but those applications unfortunately do not show that the speedup, the full speedup, is actually exponential. Probably show that there is a polynomial speedup, or the speedup might not be really known. It might depend on the particular instance of the problem. All right. So one of the examples that I already mentioned was estimating hidden times of Markov chains in our paper. There's papers by Nathan and others on machine learning for solving problems related to least squares estimation, for example, by applying the pseudo inverse, and it's been used in other algorithms for solving certain linear differential equations. And you already heard some talks on these problems before. Finding more applications for quantum algorithms like this, I believe, is really important, especially if we indeed find problems for which an exponential speedup is obtained. There's been more recent work by the authors are here in this conference about fast inversion precondition, quantum linear system solvers, and fast evaluation of matrix functions, and they apply this to problems in quantum physics. They appear to be fairly efficient quantum algorithms, but I think the search for other applications where this nice quantum speedups shows up is really important. All right, so there's been more recent ideas for this problem. Some of those ideas are what they call, these variational algorithms, related quantum algorithms to this problem. Some of the claims that these approaches may be useful for niche technologies, may solve the quantum linear system problem faster, may not need the quantum error correction because shorter depth quantum algorithms and so on. But well, in principle, they seem to be nice and simple ideas. I think it's valid to ask whether they work or not. So just to see, this is one, an example of this variational approach. It's not the only idea that is you can find in the literature. There, the idea is to prepare, for example, a number of quantum states, and then at the end, you make some sort of processing, and that processing comes through the evaluation of some cost function. And particularly for the quantum linear system problem, that cost function certainly is going to depend on the matrix A and the initial vector B, some observable that you can compute on the state, and then you obtain some estimate for this expectation value. And there's going to be a global minimum for the cost function. And whenever you don't attain that global minimum, you will reject the state. You'll say that state is not a solution to the quantum linear system problem. And whenever you find the global minimum and you know what the global minimum is, for example, might be a 0 value for the cost function there, you stop. So the question is, do these approaches work? Do they require a costly optimization loop? They require computing cost functions with high accuracies. What's the running time and all the things? And not many times you find that all these analyses are actually, included in detail in those papers. So why are these approaches even suitable for these devices, right? So all of these are valid questions. So to analyze these questions, we reduce the problem to one of quantum state verification, all right? And explain a little bit more about this in the next few slides. So this is only part of the motivation. I think that regardless of these approaches and these ideas, the quantum state verification problem is interesting in itself. As it can tell us something about other things and complexity of the problem and so on. So in the rest of my talk, I'll introduce the quantum state verification problem in the next few slides, and I show that indeed quantum state verification for this problem is expensive. Okay, and one implication is that these recent ideas actually do not work that well and shouldn't provide better algorithms than what we need before. So how is the quantum state verification problem defined? Well, this is simply the following way. Say that we are in some instance of the problem, our target state is X, and we are giving one copy or many copies of state rho that is close to this X or far from this X. What we want to output from quantum state verification protocol is a bit such that if the state is close enough to the solution, that bit is going to have high probability of being 1. If it is far, that bit is going to have large probability of being 0. Protocol quantum state verification protocols for this problem might look like this. They implement various operations and they interleave applying this state unitary operation, the other procedure UB. Those come as control operations implementing, we're assuming that we have control versions of those and even applying the inverse is allowed here. And our goal is to really set for this work what is the minimum number of this state preparation unitaries that we need in order to produce that gap on the bit that we need for the quantum state verification. So the main theorem is that for any instance of the quantum state, the quantum linear system problem, specified some matrix A and some vector B, there is a lower bound on the number of the unitaries that we need. And that lower bound actually scales with the condition number and scales with the norm of this vector that we want to, of 1 over A acting on B. Okay, so what does this mean? Let me see, I cannot switch slides for some reason. There you go. Okay, okay, so on one side, we show that this norm that enters in that complexity typically scales with the square root of the condition number. So when we put the result all together, we're obtaining that first verifying whether we're having the solution of the quantum linear system problem or not. We're having a scaling that is scaling at least with the square root of the condition number. Okay, so the number of resources for quantum state verification can be very large, especially if the condition number is large. So it can be indeed shown that this lower bound can be obtained by using one of the known algorithms, the HHL algorithm. Things are actually worse for a restricted class of verification procedures called prepare and measure. There we cannot apply the unitary state preparation unitary, but we have access to multiple copies of the state P. And in that case, we obtain even a quadratically worse cost on the number of how many copies we need for the quantum state verification protocol to work and produce this gap in the bits. In that case, as I said, the result is quadratically worse in the sense that now scaling with the condition number square over this norm of the state square. And if you remember this, typically it was going with the square root of kappa, square should be kappa. All right, so these protocols used actually by these variational approaches can be cast as a class of these quantum state verification protocols of this type, prepare and measure. And we assume that the typical complexity will be at least linear in kappa. Okay, and in fact, you could expect that variational approaches to worse due to other types of noise that appear like sampling noise appear due to the math. So the basic idea of the proof is really simple. What we do is we start from some state B for which we have a state X as a solution. So if I'm given a state rho or multiple copies of it that are close to X, by definition, by assumption of our quantum state verification protocol, that protocol should accept rho for this instance with high probability. For each instance B, we can create a new instance B prime such that maybe the initial states are not that far from each other. However, B prime has a solution X prime that is almost orthogonal, is very distant from X. So if now I have a quantum state that is close to X prime, then if I run the quantum state verification protocol with the instance parameters for B prime and the same A here, then it should accept that state with high probability. But that protocol, you can show if B and B prime are close to each other, those two protocols are close to each other. And therefore, by contradiction, you are showing that states that are close to X prime are going to be accepted by the original protocol as well. All right. So in the paper, we show how to create these new instances. Those new instances have this nice property that B and B prime differ by this quantity here. And we have to create the gap in the probabilities of the quantum state verification protocol. We have, the distance during the protocol has to go with the inverse of this quantity, and that is how we obtain the result that I showed in the first video. All right, so the actual proof is a little bit more technically involved because this output bit can be output after any number of uses of the unitaries, and probably that number might be random. So all those technicalities are there in the proof in the paper. And the quadratically worse bound is simply a result of the fact that the trace distance between m identical copies of two states increases only with the square root of m rather than linear. So those were results for quantum state verification protocol that should work for all states. These variational approaches actually, they accept a state whenever the state is very close to the solution, but that is not true for all states that are close to the solution. Some of them might be rejected, and this is because of construction. We also show that this same limit applies for these other approaches in which quantum state verification is done via the computation of cost function. All right, so I'm done. I think I'm right on time. So a few conclusions. I think we all think quantum computing is promising. There are several quantum algorithms for problems in linear algebra with significant speedups, and I showed one of them here. So in particular, the ones that I show are for solving the so-called quantum linear system problem. And certainly, some of the techniques can be generalized to apply other operators for solving other linear algebra problems, other operators of the matrix A, say, to quantum states. So the advantage of this linear combination of unitary algorithms that the complexity dependence on precision, as I showed, is only polylogarithmic, exponentially improving previous algorithms for this problem, and indeed further improvements are known. The advantages of the adiabatic approach is that it doesn't require many ancillary qubits, and the problem reduces to a simple Hamiltonian simulation problem. And that is interesting because we were able to bypass this technique of variable time amplitude amplification. So it would be nice to explore further whether these adiabatic approaches are indeed a way of avoiding variable time amplitude amplification in other quantum algorithms. And certainly, I think there's more room, more work to be done in terms of understanding the applicability of this problem to problems of interest, perhaps along the lines of physics simulation. Thank you.